here we are once again. This is the Physics 105A video lecture. Physics 105A video lecture 15. And let's just start off with some announcements since we're getting close to the end here. So 15, 16, and 17. Those are the remaining lectures. And this one here, next Wednesday, that would be all review. Okay. So I'll do some new material on these two. But as far as the exam material goes, we're close to everything that had to be done. So we actually did quite a bit of great stuff. We ended with that scattering problem, the Rutherford problem. So I want to make sure everyone has enough time. And let me just give some general advice. First of all, 12 people took the exam. I hope and expect I'll have all 12 together next semester. Okay, this is a 2-semester class and we've accomplished a lot. We're going to accomplish a whole lot more. Okay, so I'm looking forward to that. And so treat it like that as well. Don't get discouraged. Some people, there's reason to be discouraged for various reasons, but put that out of your mind and try to look at it as the entire 2-semester course that we're going to take. One good piece of advice is concerning the notes. You can go back to the original notes and all the video lecture notes and just write them out. The thing is, the course has been constructed with a good logic to it. Everything should fit together nicely. If you expand your notes or first of all, just leave a lot of space in there, then you can fill it in. Ambiguities, mistakes, what have you, missing calculations can eventually be filled in and you'll have a very nice set of skills and a good mechanics foundation. Good, so that concerns the general discussion here. Now, as far as these 2 lectures are concerned, it's moving on into next semester's material I would have done next semester typically. So what did we leave out this semester? We left out the complex analysis. Okay, so that's a note that you can put there. The complex analysis would have tied together all of our Fourier material, and it would have also tied together the, or it would be very, hold on a moment. Hey, I'm giving a lecture right now. No, sir. Hey, how do you like that? Okay. Nothing phases us, okay? It's one take, no edit. Where was I? Oh yeah. The complex analysis ties together all of the Fourier business that we've done so far. It ties together with the oscillations chapter, and it also is tied together with the integral theorems. But we'll probably tackle that next semester as a section because it's such great material. But don't worry about that. Everything we did with the Fourier and the oscillations stands on its own plenty fine, plenty well. Good. So what's to come now, and which is just good work in terms of what we've done already, after we've done the scattering, is the, here, I'll underline this, is the point mechanics it's called. So we're going to do mechanics of systems of many particles. Okay, so this is some terminology. Point mechanics and this is systems of point particles where you just have a large number of them, n, okay? So I'll just write systems of n point particles. That's what it means. And we can get rid of this now. Okay, n point particles. And what we'll tackle then is the conservation laws. Typically I save the scattering problem until we've done systems of point particles and conservation laws and collisions, but actually the scattering fits in so well with the central force problem. And the central force problem we had reduced to a two-body, from a two-body to a one-body problem. So fits in well there. It's actually pretty ideal the way we did it. Okay, point mechanics, systems of endpoint particles, and conservation laws. So we'll see how far we get. We're in no hurry. We've actually covered a good chunk of what we intended to do this semester, so everything else frosting on the cake. Now, so how do we set this up here? We're talking about n particles, and 2 was enough trouble, but we can just draw a picture here with particles 1 through n. So each of these is a point mass. There's a vector to it from some origin. So that's r sub 1, and that's r sub n, and there are a whole bunch of them. And these particles interact with each other. So we already set this up with our two-body problem originally. And this is just a generalization of that. So we have n particles, 1, 2, 3, 4, and n. A whole bunch of them. They have the position in space, and of course they obey Newton's law. So for the ith particle, we can write this: m sub I r sub I second derivative. So mass times acceleration is equal to f sub I equals 1 to n. Okay. And yeah, now you want to tackle that thing. Apparently we need to know a little bit more. But when there were only 2 particles interacting via a central force, we were able to solve the thing completely. That's our big accomplishment so far. So what can we learn about systems like this? The first thing we're going to do is talk a bit about what's on the right side here. And I'll just do that by rewriting this equation. M sub I second derivative equals f sub I external. So I'll write external up here. Plus, I'm going to write j equals 1 to n. J is not equal to I. F sub ji or ij, it doesn't really matter, I'll write ij. Okay. So what have I done here? I've taken this force on the ith particle, which is just one of these, and broken it up into an external force that is, say, acting on all of these, and then the sum of the internal forces. So these are the external and internal forces respectively. And the internal forces are the actual interactions between these various particles. And the external force, you can imagine this collection of particles held together by springs. Okay, so those will be all their internal forces. And then I could throw the whole collection across the room. And then the external force would be the weight, right, the gravity on the whole thing. So that's what we mean by the internal and external forces. And we're going to give examples of these, namely the ones we know, gravity and the central force. So I'll put right here underneath as an example, if I only had 2 particles, my example is the stuff we did to get to the central force problem. I could say m sub 1 r sub 1 second derivative is equal to, and ignore the external force for a moment, it would be, for gravity, be minus g m1 m2 divided by r1 minus r2 squared. And then I would have to have a direction vector, r1 minus r2 divided by its magnitude. Okay, these expressions start to get a little hairy. But if you write it down and take a good look at it, you've got the minus sign, and since this vector is pointing at 1, at the particle number 1, the minus sign says it's pointing away from it, namely at the particle number 2. So that would be an example of it. And the second equation, remember we had I equals 1 to n, the second equation is going to be the same thing with this vector reversed. Okay. So let me go ahead and put that up here. So we would have n sub 2, or sub 2 second derivative would be minus g m1 m2. I could write, r2 minus r1 squared, same thing, magnitude, and then that unit vector, r1, r2 minus r1, magnitude. Okay, we're gonna have to write those out a little bigger, or make sure you make them clear to yourself. But that's just to show that formally we can do this. Okay, we can do this no problem at all with the forces that we know. In fact, I'll probably also even write out the n particle version of this. Okay, so good. Let's go ahead and make a little space here. What have we learned so far? We're dealing with a system of point particles. There are the forces, the interactions between the particles themselves, and then if they're in some external field, it's the system that acts on all of them. It's the force that acts on all of them. Okay, so I'm going to clear up the board and probably replace some of this. The green board is nice, but it's a little small. It's all right. I'm going to do this example again. So let me replace what we have here, r minus derivative, external force plus the sum of all of these, j 1 to n, j is not equal to I, j. So external, internal forces. Let's do the example from gravity. So we just did the 2 particle version. So I'm going to write for n gravitating particles. Say we've got a solar system worth, another thing like that. So for n gravitating particles, we're going to say that the force on the ith particle, and this should make sense, it's going to be minus g mi mj over r sub I minus r sub j. So that's a difference vector magnitude squared. We've worked with this thing before too, because that was our vector r in the 2-body problem. There was a difference vector, but now it's for the whole set of these guys. So this is going to be j equals 1 to n. But j is not equal to I because that's that's the force on itself. So it's all of those n minus 1 other things. And then the vector here is going to be ri minus rj divided by its magnitude. This is just a unit vector. And since a pair of vectors like this points at r sub I, right? So the force is pointing away from r sub I, namely r sub m sub I is being attracted by the other one, so that minus sign gives us the right thing right there. Okay, so there's the force. And to make life easier, we'd like to have a potential energy as well. So what's the potential energy to this thing? So there's the force and the corresponding potential energy. It's going to look like this. U equals minus G. Actually, leave some room here. Okay, I'm going to fill something in. So minus, now leave some room, G, Mi, Mj over Ri minus Rj. If this were two particles, we'd be done, okay? If this were two particles, we'd be done, but we have a collection of n particles, and we have to do the following. A double sum and a 1/2 in front, I equals 1 to n, j equals 1 to n, I is not equal to j. So I'm just making the claim right now, I'm putting that there. This is a classic homework assignment that we're probably gonna put off, we'll put this off till next semester, although you guys may monkey around with it. But yeah, the homework assignment would be to show that the appropriate gradient of this thing gives us this expression here, okay? So I just wanted to make sure I put something concrete down before we just follow the theoretical development a little more, okay? So these are concrete examples. N gravitating particles, you've got this force, got this potential energy I'm claiming, you can prove it, we'll prove it later together. So that's the reason for this example right now, so that it's just not all theoretical. This is a concrete example. For two particles, we've actually done it, okay, but n particle a little more challenging. Good. This is what we're going to continue on with. So you'll notice if there is a potential energy, okay, I've given a concrete example. Now I'm going to say something about the general form of potential energy. So for potential energy functions, what we're looking for and what we're looking at is a potential energy function of all of the coordinates. And this is, right? This is one of all of the coordinates such that f sub I is equal to minus gradient sub I of this potential energy u here. So what do I mean by gradient sub I? What I mean is that I go to the ith coordinate vector here, whichever one it is, between 1 and n, and take those three derivatives, right? So say you were at r sub 3, it has an x, y, and z coordinate, and you would take the gradient, the x, y, and z partial derivatives. So that's what's meant on that right there. Okay, so we're looking for a potential energy function that will have this standard property, but for I equals 1 to n. And I've given an example of one here and the corresponding force, just to be concrete. So now what we can talk about is what I promised, the conservation laws. We're going to talk about energy conservation first. Because with a system of many particles, your only hope at all of getting some general solutions is with conservation laws. We saw that with two particles already. I should say something else before we move on in terms of our hope of getting solutions. With a complicated system like this, you want to be able to set it up and then confidently say some general things about it, which we will all semester. But if you were into numerical integration, then you'd have to carefully set up a system of particles and then see if you could numerically integrate it, say to predict the behavior of such a system like that. Good. So I will move on now to the energy and the conservation of energy theorem. That will give us a fair amount to do. So when we have a potential energy function, then the energy, the mechanical energy, total mechanical energy, can be written as the sum of all of the individual kinetic energies of our set of particles, I equals 1 to n, plus this potential energy, which is a function of all of them. And by the way, the forces that I just erased were also implicitly and explicitly functions of all of the coordinates. So when I had f sub I, it was a function of r sub 1 to r sub n. Yeah, so this is the energy. And to prove that it's conserved, I'll just indicate this r sub I dot squared is x sub 1 dot squared. So it's the scalar product of the velocity with itself for each individual. So x sub 1 dot squared plus x sub 2 dot squared plus dot squared, okay? It's the square of the velocity for each individual particle. Oh, what am I saying here? Let's do this differently. So x sub 1, y sub 1 dot squared, z sub, and not 1 but I. Here we go. Okay, messed up in the indices. There we go. The vector r sub I has components x sub I, y sub I, z sub I. Dotted with itself, that's what you get. These are v squared. Okay, so let's go with dE dt, the complete time derivative of this object here. And under this summation, I equals 1 to n, we would have 1/2 m sub I, and then we'd be taking the derivative of this thing, which is the derivative of this one here. So I'll write that. That would be 2x sub I dot x sub I double dot chain rule plus 2y sub I dot derivative to z sub I second derivative. Okay, so I've taken that, and that's going to simplify. Over here, I have to know something about the chain rule for many variables. Many variable chain rule, because we're thinking of r as a function of t, since we're taking the derivative with respect to time. So what we're going to have is the sum of these individuals, the sum of the gradient sub I of u, and then the inner derivative, which would be the dot product with the r sub I dt. So that's a chain rule in which I take the derivatives of the I of variable here, and then the inner derivative with respect to time. Okay, this one may need a little working out as well. Formally, of course, I can plow right through it. What do we have here? Cancel the 2's. And then what you see is we have a dot product between r dot and r double dot, because this is from r dot, this is from r double dot, likewise here and here. So what I can write this first sum as is 1 to n, m, 2's already canceled, so I, r sub I dot, inner product, second derivative, and this right here gradient sub I of u dotted into r sub I dot. Okay, one more line I'm going to squeeze in the bottom here. Namely, what I find is that I can pull out r sub I dot here, and then I'm left with m sub I, r sub I, second derivative, plus gradient sub I of u. Okay. Yeah, what does that equal to? Well, here we're done. This is Newton's law. If you look closely, this is the negative of the force. Mass times acceleration minus force, of course, is equal to 0 by definition. So each one of these is individually equal to 0. I mean, not by definition, by our assumption. Newton's law is true. Okay, that's the world we're living in here. So yeah, this whole thing is equal to 0. And that means that this energy expression is conserved. Yeah, so there's a fair amount going on here. This would be good to tease out a little more in a little more detail if you're not familiar with the chain rule for functions of many variables. So I think I'll do a little bit with that before we move on. But this is our first conservation law, energy. Mechanical energy is conserved in an n-particle system if you can find a function whose gradient gives you the force, and that's our potential energy. Everything that we stated about potential energies last semester is going to be required for here too, the path independence of the work function and so forth, okay? But here we're just treating this as an antiderivative. Okay? If we find it has requisite properties, we're good to go. All right. So maybe a little more discussion of this. And what I'll do is I'll just leave this and we'll direct our attention to that. So chain rule functions of many variables. So you're used to f of g of x equals f prime of x of f prime of g of x g prime of x, and we do with the function of time, we get the same thing as well. Okay, so let's look at when we have f of x1 of t, x2 of t, all the way to x of n of t. Okay. The rule here is that if we're differentiating this with respect to time, we're just doing a chain rule for each one of these, just as the standard recipe, except we're summing them all up. Okay. So what we then have is a sum of all of these df dx of I, and since f is a function of many variables, I'll just say vector x of t. Okay. But from the chain rule, we get the dx of I dt. Okay. So it's just a single chain rule for one of these slots, but there's n of them, and you have to sum them all up. So this rule is interesting. It comes from the fact that the derivative is a linear operation. It's a linearization, so to speak. And so this sum here is really, in the more general mathematical world, it's a type of matrix multiplication, or a type of scalar product. So that's the reason why you sum all of these, just like when you have linear operators as matrices, your multiplication of the operators turns into the summation. Okay, so yeah, this chain rule is used more and more, especially next semester, so we get used to it. And that's actually what I did right here. So if you want to tease that apart, you'll find out that each one of these was 3 of these here. Okay. So I went over to the ith particle, I had xyz like that. Okay. Good. So now we really have the conservation of mechanical energy for the multi-particle system. You know, I think we have time. We'll do one more, because conservation laws are pretty interesting. And so I'll erase this. let's go back to, okay, we have energy. So let's go back to our system of equations. F sub I, external force plus sum over F sub I. J equals 1 to n. Note the summation, by the way. It's the ith particle. There's a tag I, there's the I, and I'm summing over all of the j's. Okay, so this thing remains as I'm with a subscript I on it, and j is not equal to I. Good. So what we're going to do now is this sum over I equals 1 to n for this whole expression. So next, we'll say the sum over m sub I or sub I, second derivative. We end up with the sum f sub I of the external forces. And then here we're going to have a double sum. We already had one sum, f sub ij. And we had j equals 1 to n. Now we have I equals 1 to n. And again, I is not equal to j. So we're going to look at this, analyze this expression. If this one's true, then this one's also true, right? Equal, equal. So what we're going to note about this sum here is that we have f ij. If we take out a pair ij, say 1 and 3, 3 and 1, fij is going to be equal to minus fji. Because those are the forces between I and j, these two particles, and we have Newton's third law. And this is just the expression of Newton's third law. The force between these two particles are equal and opposite. Okay. So by Newton's third, and what that means is this double sum sums away to 0 pairwise. Okay. Take an I, get the other j, add them up, fij plus fji equals 0. That means the double sum vanishes. So the double sum vanishes because of Newton's third law. That's another way of saying all of the internal forces vanish. Okay? The sum of all the internal forces vanishes. So what are we left with if these vanish here? We're left with sum over m sub I, second derivative, is equal to the sum of the external forces. And haven't we seen this before? This is the net external force, or the sum m sub I equals F net external. Okay, so what does that mean? It can mean a number of things. Suppose the net external force is 0. And we'll start with that and then keep going. So first of all, we just have this identity, so to speak, this equation. Actually, there are a couple directions we can go with this thing. That's right, I equals 1 to n. We'll go ahead and do this, suppose the net external force is 0, because that will put us right into contact with something we've seen before. So if F net external equal to 0, then of course the left side of this is equal to 0, and we can immediately say that the time derivative here is equal to 0, because the time derivative here just gives us our second derivative. And of course that means that my expression here in parentheses is constant or conserved. This would be the conservation of linear momentum for a particle system with n particles. So in this case, we would say capital P is equal to the sum of all the lowercase p sub I is equal to the sum of n sub I r sub I dot. So I just write this in a string of, we call these here equals constant. So that's conservation of linear momentum. And that's our second conservation law. Second conservation law right there. There's a little more that we can do with this as well, namely introduce the center of mass. I think I'll introduce the center of mass and then leave it at that as a good place to take a break. So we get conservation of linear momentum. We have, in fact, let's do this. We have energy. Energy, the scalar, is one quantity, and we have linear momentum. That's a vector, so that's three quantities. So we now have four conserved quantities. Four conserved quantities for all those n, 3n variables actually. N particles, each one has three coordinates, so we have 3n equations actually. So yeah, how about the center of mass? Everybody's seen the center of mass before, so we'll just put it into perspective here. Center of mass I'm going to define like this. R sub Cm is equal to the sum m sub I, R sub I, divided by the total sum of all the particles. So everybody's seen this before, I trust. So there's our center of mass. We're going to do this. And one thing I can do is take a derivative and take a second derivative of it. Okay. But what I'll do first is cross multiply this, and then I'll have the sum of m sub I. And then I'm going to take two derivatives, so r center of mass, second derivative. But what is that? That's sum of m sub I, r sub I, second derivative, right? So two derivatives. But this is something we just had on the board and I erased. Namely, this was F net external force, the sum of all of those individual forces. So here's what we have. We have, I'll just use the total mass, center of mass, second derivative, is equal to the net external force. This is a really powerful theorem actually that we always use, but now we're just made aware of. I'll put a box around here and admire it. For point mechanics, this is really important. Okay, so what do we have here? I hope this is legible. We've got the total mass times the acceleration of the center of mass is equal to the net external force. This is true for all of our examples that we've been doing. If I kick a baseball around, there's a baseball, maybe not, okay. Any extended object that I launch if I'm treating it as a point mass, I often am, I'm claiming that the center of mass of that thing is what's doing its parabolic trajectory, for instance. Okay? So it doesn't matter if this is a collection of little objects connected by springs, okay, some complicated, chaotic little thing. If I launch it here in an external force, right, the net external force here is just the weight because we're in this room. Then this thing's going to launch and follow its parabolic trajectory. And so the point mechanics for many particle systems is completely consistent with your general expressions that we've been doing all this time. Right? We've been doing point mechanics, but we often think, okay, throw a baseball, throw what have you. Okay. So that's the general expression. More to say about this, but that's where the point mechanics formulation comes in. And by the way, what was required for this one is Newton's third law. The sum of all the internal forces cancel. Okay, we're going to leave it at that. I'd rather make these lectures not as long so that, of course, I almost filled the hour again. But the idea is that if you keep the lecture a little shorter, then you can look at it more than once and fill in all the missing stuff. Be that as it may. So we'll pursue this a little bit more next time. We're going to look at angular momentum and conservation law. Then we can put it all together and put a line under it. That'll be our semester's work. Okay, so be confident, take good notes, and we'll see you next time.